Hi, and welcome to a video on absolute convergence versus conditional convergence within an infinite series here. So what we're going to look at is, and I'm going to sort of jump down to this bottom part right here first. If we have this alternating series of, where the alternating condition, -1 to the n, or maybe it's -1 to the n plus 1, something like that, and then we have our so-called series afterwards, or that pattern, if you will, that sometimes we have to write. So if this is my infinite series, and again, something that we're assuming is that we're starting at 1 or 0 or 2 or whatever, and we're going to infinity. So what I'm going to do is test the positive series. And what happens is the alternating series, if you think about it, where I'm alternating plus, negative, etc., versus the series of all positives. So I'm talking about the same values within that series. Which one is going to be bigger? Well, obviously, if I'm just adding all terms together, that's going to be bigger than if I'm adding a term, subtracting a term, adding a term, subtracting a term, right? So this is going to be smaller. So this goes back to the idea of if I know that I have some series right here and it's convergent, and I know I have a series smaller than it, it also has to converge. Because again, convergent means that I can find, theoretically, some finite sum for that infinite series. So it's a finite value. And so something less than finite also must be finite, right? So if I look at that positive series, so if I just drop the absolute value or drop the alternating condition, so to speak, taking the absolute value of that, and that converges, I say that it will absolutely converge, which means both the positive series and the alternating series converge. But sometimes what I notice is that that positive series will diverge because when I add, it gets too big, and so it diverges. So then I do need to use the alternating series test to show, does it conditionally converge or does that series diverge? The conditional convergence means that, for example, and I can use a series that we're familiar with, but I know we're going to talk about that one here in a minute, but maybe my harmonic series or something like that. But we'll look at an example here in just a second. So one thing also to note is occasionally a series may have both positive and negative terms and not be an alternating series. So I really want you to focus on this alternating condition piece. So for instance, when you have trig, like sine of n, right, over n squared, as n grows and it's going through each quadrant, it's positive in quadrant 1 and 2, but then it's negative in quadrants 3 and 4. And so it's going to have both positive and negative terms, yet that is not an alternating series. Okay, so if you see the decimals written out, that does not necessarily make it alternating. We need to make sure that that alternating condition is on there. All right, so let's look at a couple examples here. So test the following series to determine whether the series converges conditionally or absolutely, or does it diverge? So now I have three options, whereas before we were just saying, does that series converge or diverge? Now if it converges, I'm saying, did it conditionally converge? Meaning, did I have to put the condition of -1 to the n or -1 to the n plus 1? Did I have to put that alternating condition on it in order for it to converge? Or does it, excuse me, converge all the time? Absolutely. Okay, so what we're going to do is we're going to look at this, make sure that, yep, it is an alternating series here. So now I can say, let's just check this positive series. So if I look and replace that -1 to the n plus 1 with just that +1, this series, 1 over n, is the harmonic series, which I told you we would talk about, right? 1 over n. And so this series diverges. So the positive series diverges. It has a sum that will continue to grow. So what that means is now I know that it cannot absolutely converge because this positive series does not converge. So both are not convergent. So I still don't know. Does it conditionally converge or does this beginning series diverge? Again, this is the series that we're trying to talk about, right? So what I want to find out is, now check using the alternating series, and so I'm going to use the alternating series test. And so the alternating series test has two parts to it. I like to do the second part, or what people usually list as the second part first, because if this part isn't true, I don't even have to worry about the inequality, right? So I'm going to show that the limit as n approaches infinity of my series 1 over n, and that is 0. So now I can go to the A part of it, or the first condition in the alternating series test, which says that my next term needs to be less than or equal to my current term. In other words, you're working within that decreasing function, so to speak. So I will put 1 over n plus 1, I'm substituting in n plus 1 for n, will be less than or equal to 1 over n. I'm going to multiply both sides by n times n plus 1, subtract n. This is true. So I do know that this alternating series converges by alternating series test. But what I would say further is, because when I put the condition on it, when I put this alternating condition on it, it converged. But without that alternating condition, if I just took a look at that positive series, it diverged. So what I would say is it conditionally converges. Because again, I needed that condition on it of that alternating condition in order for this series to converge. It just gives us an additional piece of information about that series. So I know just by saying that it conditionally converges, I know that the positive series would diverge and that the alternating series would converge. So let's look at another one. Same directions. I'm going to say I have this alternating condition on here. So again, the better you are at doing these alternating series tests, or the more practice you have with that, I think this will make more sense as we go through. But let's just check the positive series and see what this positive series does. So drop that alternating condition and go ahead and just put a positive 1 there in that place. So then I have the series from 0 to infinity of positive 1 over e to the n. I'll write out a few terms. E to the 0 is 1. Then I have e to the 1, e squared, and again, these are all in the denominator, right? And hopefully you can see that this series is geometric and has a common ratio of 1 over e. And that ratio is definitely less than 1, which means by the geometric series test, that series converges. And so what we know is, if the positive series of this, 1 over 1 plus 1 over e plus 1 over e squared plus 1 over e cubed, etc., where I'm adding positive terms the whole time, if that converges, if that converges, then we know that if I alternate these signs and look at this, the sum of 1 over 1 minus 1 over e plus 1 over e squared minus 1 over e cubed, etc., that sum is less than this sum over here. And so if it's less than finite or less than convergent, it must also converge. So I would say this one absolutely converges. Now, if I wanted to, I could show using alternating series test that the alternating series does in fact converge as well. I'll quickly prove that for you, but this is not something that you would have to do. So if I go from 0 to infinity, just rewriting my series here. So I would want to prove two things. I would want to show that the limit as n approaches infinity of 1 over e to the n, that absolutely is 0. And then I would want to show that my n plus 1 term will always be less than my nth term. So I have 1 over e to the n plus 1 less than or equal to 1 over e to the n. Again, this is sort of extra, if you will. I don't need to necessarily do this each time. So if I multiply both sides, I have e to the n less than or equal to e to the n plus 1. And e to the n plus 1 is really e to the n times e to the 1, because remember, when you multiply with the same base, you add your exponents, so that's how e to the n plus 1 is arrived at. So then I can divide both sides by e to the n, and it's saying, is e greater than or equal to 1? Yes, it is, so this would also converge. So what I can see is I got both series to converge, right? The positive plus 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 series and the alternating series plus negative plus negative plus negative. So I would say this absolutely converges. A lot of people also put in their mind that absolute convergence has to do with the absolute value. And so this positive series, right, is really the absolute value of your series. And so that might help you as well. Again, none of that to the right was necessary. If you say the series absolutely converges, both, again, the positive and the alternating series will converge. So I hope you found that helpful. We'll talk about that a little bit more as we go through the ratio test, but for the most part, it really is linked to this alternating series test. So I wanted you to see that right after you tested for convergence using the alternating series test. I hope you found that helpful. Thanks for watching.